Okay, hi everybody. So we just took this quiz and I was grading it and I noticed some common errors. So I'd like to go through with them. First, let me just point out, so the comparison test has to do with two infinite series that most of us gave the names A's and B's to the terms. But let me just point out something. So the series is this thing. Maybe it's the sum from n equals 1 to infinity, maybe n equals 0 to infinity. Okay, and then there's the sequence of terms, namely the a sub n's themselves. Okay, and so remember, a sequence is a map from n to a sub n. So a sequence is like, we can also think of it as the image of this map, which is just all the values for every natural number. And so you see that a sequence is either a map or like a huge list of infinitely many things. And it's certainly not a series. A series is a number. Okay? If this series exists, it is a number. Maybe it's a complex number if these terms are complex numbers. Maybe it's a real number if these a sub n's are real numbers. But it is one number. Whereas a sequence is infinitely many numbers, one for every natural number, or maybe it's every positive integer, etc. Okay, so then there's also, associated to a series, there's the sequence of terms, and there's another sequence. Usually denoted S sub m or S sub n, depending on what you want to name the index. Now, what is S sub m? Well, we have to say that it's a1 plus a2 plus a finite sum. Okay. If you want, you could write S sub m is equal to a sum of the a sub n, where n goes from 1 to m. Okay. But in particular, S sub m is not equal to the sum of infinitely many a sub n's, okay? It's not. It's just equal to adding up m of them, okay? And we can do this for every m. Hence, this is a sequence. It's a whole infinite list of numbers, the partial sums for any number, any finite number of terms. Okay, so these are three very different things. They are related, of course. The partial sums are just finite sums of these terms, of these things in this sequence. And then this series is the limiting value of the partial sum sequence. Okay, but notice that this would be a number. This would be a sequence, a map. This would be a sequence, a map. So these are not, these are infinitely many numbers. Whereas this up here is just one number, the limiting value of this convergent sequence if it converges. Okay. So in particular, I think somebody had said that the a sub n are increasing. That would be wrong. In fact, if this infinite sum exists, then the divergence test says that the a sub n have to actually converge to 0. They have to go to 0 for us to even have a chance of getting out a finite number, the infinite series, or the sum of the infinite series. Okay. So in particular, if the a sub n's are all positive and they're going to 0, they're actually definitely not increasing. So I think somebody had written the a sub n are increasing, the b sub n are increasing. But no, actually, to be correct, the a sub n are not increasing. The a sub n are not increasing, I think. But either way, yeah, okay. This I had seen written. This does not make sense, okay? In particular, S sub m is not an infinite sum. S sub m is a finite sum. T sub m is not an infinite sum. This is false. To make it correct, you could say like that. Or you could just write B1 plus Bm. That's sort of easier to me. Okay. Let's look at this one. Assume. Okay, so this is the name of the mth partial sum. So I'm to make this be correct, this must be a finite sum over here, which is just rewriting this and this are writing the same thing. Now this equal sign is definitely wrong, because I'm pretty sure that t was meant to be the limiting value of the sequence of t sub m's. Okay, the limiting value as m goes to infinity or whatever. Yeah, okay. Let's look at this one. So the sequence, this, I think the person meant something like this. This is just wrong. This would be called a series. Okay. Now, if you could also say the sequence, and then if you put a finite sum like this, for m in n, now we have a sequence. For any natural number, we have a number, the partial sum, and really this sequence has a different name. Usually we call this S sub m, the sequence S sub m. That would be okay. Okay, let's look at this one. Okay, so again, in order for this to make sense, this needs to be a finite sum. Okay, another way to write that is b1 plus dot 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 plus bm. That's fine. So both of these would be fine. But now, converges to some upper limit. Well, I think it'd be better to say has some upper bound. Okay. That's really what we needed in this proof. We needed it to have an upper bound. Now, this sequence of partial sums may have a limit. The t sub n's may actually have a limit. Maybe we call it t. And that limit would be some real number. And then we could try to claim that t sub m is actually less than or equal to t for all m. And I think it would be, specifically because each of these terms was positive. And so we're increasing, and so there was even maybe a problem about this. So this could also be made to make sense as well. But you'd have to then make a little bit more of an argument to show that it converges to some number which is also an upper bound. And so I would say converges to some number t, and then I'd say which is also an upper bound, meaning that the t sub m are less than or equal to t for all m. And you'd have to maybe argue that, which you could argue that, because these are positive. So, okay, let's look at this one. These are tricky, lots of tricky language. So I'm pretty sure the person meant like this, maybe, I don't know, maybe they didn't. But if they wrote this would be wrong. A series cannot be monotone increasing, because a series, if it exists, is just some number, the limiting value of the sequence of partial sums. It's a number. A number cannot be monotone increasing, right? Does that make sense? So the only way to make this make sense as written would be to assume that this sum was actually a finite sum. And actually this was referring to the mth partial sum. And then that sequence of mth partial sums for every little m in the natural numbers gives us a sequence. That sequence is monotone increasing. That would make sense to say. So, in other words, a sequence can be monotone increasing. A series cannot be. Okay, let's look at this one. Assume that b sub n converges. I'm pretty sure the person meant the series of, This makes sense. Assume that the series converges. I mean, that's what they meant. This is what they meant. Now, this also does make sense because B sub n is a sequence, and a sequence can converge. But, I mean, it converges to 0 if the infinite sum has a chance of converging, because of the divergence test. So I don't think this was what they were talking about. They didn't want to say it converges to 0. They meant that we were going to assume that an infinite series converges. That's what they meant. Okay. You see, it's just wrong it's very, well, it's not wrong, it's just different. You're not saying the thing that you meant to say. This is what you're meant to say. Okay. Let's look at this one. Okay, so this is tricky. You've already summed over n. You're summing over n here. This is now a number, if it exists. It's the limiting value of a certain sequence of partial sums. So it's a number if it exists. And maybe that number could be less than or equal to another number. That might be true. But certainly for all n doesn't make any sense here. This just doesn't make sense. Because we already summed over the n is gone, and what's left over is now a number. So this just doesn't make sense. So, yeah. I think what the person meant is that for all n, the t sub nth partial sum is less than or equal to some number u. I think this is what they meant, but I don't know. So it's really difficult to be precise with this stuff, and it's really important to remember that a series is a number if it exists. It's the limiting value of this sequence. This is a sequence of partial sums. And those partial sums are created out of this sequence, namely the sequence of terms